we're going to be exploring exponential functions. And for the most part today, for today, we are not looking at transformations. So we're going to be looking at just the parent function today. And so a parent function I use relatively loosely, but it's just we're going to be focused in on this b to the x today, a number raised to the power. This a isn't going to come into play. That is going to come into play tomorrow. But for today, we're looking at the b. If the b is greater than 1, that means it's growing. That means it's going up as we go to the right. If it's between 0 and 1, it's decaying. It's falling as it's going to the right. And so this is the growth. This is the exponential growth. This is what they were talking about with the COVID shot, flattening out the curve. It wanted us to flatten out that growth rate. Decay is something you'll see often in science, especially like in half-lives. It's decaying at the same amount, or we're losing that same amount of material each time as we're going through. So again, these really show up especially in medical fields and science fields and growth and decay. You also see it in compounded growth on investments. But the big thing that we need to keep in mind is B has to be positive. If it is negative, we have a problem. It's not a growth or decay. So looking at this first problem, first off, we identified that this is a growth because 2 is greater than 1. So that means if I was to sketch this graph, it's going to come up kind of like this. And so we are going to be looking to see what asymptotes y-intercept the max and the min on its interval. First thing we're going to do is graph it. So let's go ahead and look at the graph. You can see that the horizontal asymptote is lining up right here. And it is, unless there's transformations, going to be the x-axis, which means that the asymptote is going to be y equals 0. The y-intercept, where it crosses the y-axis, the way you find that is if you replace 0 in for x, anything to the 0 power is always 1. And so the y-intercept is, unless there are transformations, always 0, 1. So these are two consistents unless there are transformations. So now when we find the max and the min, we're going to do the same thing as we did with the y-intercept. We're going to plug in those values into the x and figure out the value. So starting off, we're going to find out when x was negative 3. So we have y equals 2 to the negative 3. That means 1 over 2 cubed, which is 1/8. Now let's do the next one. Y equals 2 to the 5th. 2 to the 5th power is 32. So that means that 1/8 is our min, and y equals 32 is our max. Let's do another one. This time we're going to see what happens at y equals 10 to the x. When this base gets larger, it makes the graph steeper. But as you see, the asymptote has not changed. It's still at y equals 0. And then our y-intercept, we're still going to that same spot. So again, to check it, 10 to the 0 power. Anything to the 0 power is 1. And so we have at 0, 1. So we are going to be looking at finding our max and our min, same way we did last time. So we're going to plug in those as the as the x values and find our y values. So y equals 10 to the negative 3. So that means 1 over 10 cubed. And if you don't know the trick for powers on anything with a 10, you take and you write down the number once, and then you'll put as many zeros as the power. So 1, 2, 3. So this is 1 over 1,000. Now we're going to do the same thing with the 10 to the 5th. And so we have 100,000 in this case. And so this is our max, and this is our min. Now we're going to go into a decay. So this red graph is the original graph we were looking at, so you can kind of see how it compares to it. So it's falling instead of rising. The blue graph is the new one. That is what this problem is. So when you have 1/2 to the x, it's a decay. Your asymptote, though, is still at the same location, and your intercept is still at the same location. So we have that same y-intercept of 0, 1. We have the same asymptote at y equals 0. All it's changed is the way the graph is falling. So let's look at it when we look at the min and the max and see how that looks different. So if I plug in a negative 3, oops, negative 3, not negative 2. That is going to cause it to flip the fraction, so it's going to become 2 over 1 to the 3rd, which is the same thing as 8. But when I look at the 1/2 to the 5th power, that's going to be 1 over 32, because 2 to the 5th is 32. So this is now our max, and this is our min. So when we have a decay, your max is the smaller of the two values. Your min is your larger of the two values. So in summary, if there's no transformations, your horizontal asymptote is y equals 0. And if there's no transformations, your y-intercept is y equals 0. If b is less than 1, you have a growth. If b, oops, that should be say if b is greater than 1. I put it backwards there. You have a growth function. If b is between 0 and 1, you have a decay. B can never be negative. So let's look at it if we have a story problem. It's all the same idea. This is all going back to that same equation of b to the x, or of, a times b to the x. Our starting amount is the a. Our growth and decay is our b. And our x comes from the periods. To find your growth and decay rate, like let's say I had a growth of 40%, I would first need to convert that over into a decimal. And then my growth rate will be 1 plus 0.4, so 1.4 is my growth rate. If I had a decay rate of 10%, I first change that into a decimal, 0.10, and then I do 1 minus that number, and that gives me my decay factor or decay rate, which is 9/10. Growth should always be greater than 1. Decay should always be between 0 and 1. So let's look at this one. We're going to look at two different components of it. And so your starting amount, again, remember it's your A, so 1,000, or excuse me, 2,000 was my starting amount in this case. Times, I need to figure out what my growth rate is. Because my annual rate of return is 5%. So convert this over into a decimal and then add it to 1. So your growth rate would be 1 plus 0.05, which is 1.05. And that's what goes right here. Your exponent would be how many periods. And so if it says it's an annual, that means once a year for 5 years. So how many times will that happen? It would happen 5 times. So on this one, all we have to do is type this in our calculator and we come up with a number. And that number we come up with is, oops, sorry, my computer's not wanting to work, is that y equaled $2,552.563, and you kept going on. Well, what does this 3 tell the 6 to do? It tells it to stay the same. So our answer is we have $2,552.56. And if I needed to actually write the equation of this, if I wanted the model, it'd be 2,000 times 1.05 to the x power. So this is if it wants the model. If it wants the equation, that's what it's looking for. If it wants the number, this is what it's looking for. And so this model, this equation, is what's going to help us on this next one. How many years will it take for your account to reach 3,000? And so we are going to look and see on Desmos. And so as I look along here, I went ahead and just zoomed out. I know that my y values, I need to figure out something that's happening. And so I zoomed it to where I could see between 0 and 4,000. As I scroll along and get really close to that 3,000, I notice that it's going to take me roughly 8.3. And all I'm doing is using my cursor along this line, and I can see exactly where it's going to the 3,000. It's between 8.3 and 8.31, I believe. And so 8.3 is a good approximation. And all you're going to have to do on this one is you're going to have to approximate. You can use Desmos to see it. We are not going to, oops, I forgot what the number was. 8.3. We are not going to go all the way until we have the exact number solved in these equations each year. Right now, we'll do that in another lesson. And so we're looking on this one on a table, and we're going to be looking at the population of a Linux, and it's looking at the decay rate because we're losing population. And so our starting year is at 2003 number. Our next year is 1. But we're wanting to make a prediction of what's happening in 2014. So we need to figure out how many years have passed. And so 11 years have passed. And so when we find our final answer, we're going to use 11 as our x, because we're looking at this on an annual rate. The big thing to keep in mind on the rate, when you're finding the rate, this is your end amount, this is your start, and we're dividing by the start. And it can be any 2 sequential years on this rate. And so we have our sequential periods. And so our end was 120, our start was 150, divided by 150. And when we subtract that, we end up with a negative 30 divided by 150, which gives us a negative 1/5, which when I convert that over to a decimal is a negative 2/10. And so R doesn't come directly into our equation, but it helps us create our B. And our B is 1 plus R. And so we have 1 plus our negative 2/10, which that just is like saying subtract, which gives us 8/10 for our B. In this problem, I went ahead and gave you year 0, but let's say it didn't have that. Let's look and see what you would have to do if it did not give you that 0 year. And so I'll just use that year 1 to help us see it. So we have y equals a times b to the x. So if I was looking at year 2, or year 1, excuse me, instead of year 0, starting amount, I would take and plug in. My y would be that 120. Our a is what we'll be looking for. And that is to the first power. And so go ahead and simplify what we can simplify. 8 times a times 8/10. Then we would divide by 8/10. And that gives you a is equal to that 150. Now, let's go ahead and see if we can figure out this problem. What this problem is directly asking us is what's happening in 2014. So y equals, and we said a was 150, times b, which we said was 8/10 to the x. And so for this specific instance, we are looking at year 11. And when we type that in our calculator, we end up with 12.8 approximately, which is approximately 13.